Fiber optic cable is widely used in wind farms to transmit information using light. It is a highly effective way for communication to occur between and within wind turbines. In general, the system consists of a transmitter to produce and encode the light signals, optical fiber to conduct the light signals, and an optical receiver at the destination to decode the light pulses and return them to digital form. The electrical signals can be either digital or analog. Analog signals also require use of a pulse code modulator to convert them to digital form. The transmitter is composed of an interface circuit, source drive circuit, and the optical source. The interface circuit processes the electrical signal, making it compatible with the source drive circuit. In turn, the source drive circuit varies the current to modulate the optical signal. Finally, the optical source changes the electrical energy into light. The pulses of light are sent through the transparent core of the cable. The receiver consists of a photodetector, an amplifier, and a signal restorer. The photodetector transforms light pulses into electrical signals. It is light sensitive and must be capable of detecting even weak light pulses. The amplifier increases the signals received from the photodetector. This is the primary source of electrical noise in the receiver, and the sensitivity of the receiver is dependent on minimizing this noise. Lastly, the signal restorer converts the amplified electrical signal into a form that is suitable for the interfacing circuitry. Quality transmitters and receivers work together to ensure less signal degradation across the network. However, long-distance applications also require the use of either repeaters or optical regenerators to boost the light signal. A repeater converts the light signal back into an electrical signal and then regenerates a new optical signal. A fiber optic repeater cannot distinguish pulses of light that are of different wavelengths and is less effective with multimode fibers. An optical regenerator uses a laser to optically amplify the signal. These are able to boost the strength of individual wavelengths of light and are appropriate with either single-mode or multimode fibers. Another device that may be added within the system is an optical coupler or beam splitter. This is used when necessary to channel signals to multiple locations. Splitters are distinguished by numbers that represent the percentage of signal divisions, for example, 60-40 or 80-20. The cable used within the fiber optic communication system requires different types of strands depending on the usage. Fiber strands differ depending on the design of the core in relationship to the surrounding cladding. Depending on the type of light source used, the light waves propagating through the core may follow a variety of paths. A mode describes the path of a light wave as it travels through the core. The mode or path is determined by the angle of the light wave entering the strand and the refractive index of the cladding. If the angle of the entering light wave is too sharp, the wave will not propagate through the cable. There are single and multi-mode fiber optic strands. Both single-mode and multi-mode fibers are typically 125 microns in outside diameter, but the core is significantly smaller in a single-mode fiber. Single-mode fibers are approximately 5 to 10 microns in diameter. A single-mode fiber strand is so minute that it allows a focused laser light entering the core to stay at an angle of 0 degrees without any loss into the cladding. Therefore, the bandwidth is almost infinite. It is commonly used to send data over great distances and at high speed. Multimode fiber has a larger core diameter of 50 to 100 microns. The most commonly used sizes are 50 or 62.5 microns in diameter. Multimode fiber can use either laser or LED light sources. The larger numerical aperture allows light waves to enter the core at a variety of angles. If the light wave enters the core at an angle close to 0 degrees, it is referred to as having a lower order mode. As the entering light wave deviates from 0 degrees, the order of the mode increases. The higher the order of the mode, the more the light wave will strike the cladding as it moves down the core. Consequently, a higher order mode takes longer to reach its destination. This timing difference between higher and lower modes creates modal dispersion and degrades system performance. As a result, multi-mode fiber strands are mostly used for data transmission over shorter distances. Multi-mode graded index fibers were developed to address the problem of modal dispersion. Graded index fibers have their highest refractive index at the center of the core. The refractive index of the core declines gradually, so that the value at the outer edge of the core equals the refractive index of the cladding. The higher the refractive index of a medium, the slower the light wave will travel. Therefore, this design reduces modal dispersion by allowing light waves in the outer regions of the core to travel faster than those in the center of the core, causing them to reach their destination simultaneously. This reduces signal loss. Historically, single-mode, multi-mode, and multi-mode graded index fiber strands were made of glass. Now, plastic optical fibers have been developed that offer the same effectiveness as glass multi-mode fibers. Plastic optical fiber is much less difficult to install and maintain, making it preferable in many situations.